And welcome, functions folks. We've got a kind of a weird day today. Um, uh, the what makes it weird is there's a big chunk of time now. Not just the 3 minute review. This is going to be a lot longer than 3 minute review, where you do a whole bunch of work. So if you haven't done this function review or rates of change sheets, the function review you only have to do this number 6. Um, and then the rates of change lesson part is really just review of stuff you already know with a different name perhaps. And I want you to do that work first, and then it's probably about 20 minutes worth of work or so, and then you watch this video and then do the lesson and the homework. What makes this different is usually this is all we do, right? That's a typical day for us now. But this idea of you doing about 20 minutes worth of work, whether you did that at the end of last class or before you watch this video at night, it's going to be a little bit of work for you. But the video shouldn't be too bad, I don't think. I'm going to zoom through taking up the work you did on the functions review and rate of change sheets very, very quickly. We can discuss it in class and then get to the lesson. So if you haven't done that work, please stop the video and do that work first. It might mean that you have to watch the video in class, but so be it for today. Um, Again, I'm going to take this up right now. You should have tried it. At any point, if I'm going too fast, just stop, right? Um, Typical sort of example from grade 9 where, we see the relationship and they're all linear relationships. There's no curves here. And we're asked to answer these questions. And nothing too difficult, I don't think. Um, the one thing I wanted to mention, the the slopes, right? The slope of each line segment, if it's going downhill, it's decreasing. We see those slopes. Um, and the M1, M2 here, they go with each of the segments of the graph. So that's M1, this is M2, M3, and so on, right? In case you were confused about that, and hopefully you got the right answers, or same answers as me. Hopefully they're the right answers. The one question that I did want to mention, which is weird, is part D. How fast was Sim walking at the 35-minute mark? So at this time right there. Well, that's a bit of a strange question because we calculated the interval um, from 30 to 40, right? From 30 to 40, he was traveling 40 meters per minute towards home since the slope, and it says then since it's a constant rate, right? Since it was a constant rate, then over that interval, the slope was 30 to from 30 to 40 was 35, 40 minutes meters per minute. That means at each moment in that interval, it's traveling the same speed, constant rate of change. Now, which begs to differ if it was changing, right? So say that was from 30 to 40, and we could calculate the average rate of change, which is what we're up against today. But then at the 35-minute mark, what speed would he be traveling? Well, we don't know. It changes every moment. And this is a big question, not only in our course, but in calculus as well. And that would come up in the lesson. Taking up the rest of the stuff, we've got 3 walks, Ferd, in his motion detector. And you see I've done them in green, blue, and red. So check your answers. This idea of all of them are walking away from the motion detector, but you can be more specific, right? Constant rate, slowly at first, then more quickly at first, and then more slowly. I gotta answer the phone. All right, I'm back. Wrong number. Can't remember what I was talking. Oh yeah, the 3 walks, and then we sort of had to calculate some slopes. We had a table of values and then calculate some slopes. Um, and notice that this is the D value over the T value, meters per second. And notice that backs up what we talked about earlier, constant rate. But here it was slowly at first and then more quickly, or quickly at first and then more slowly, and it backs us up exactly. Calculations match numerically with our verbal descriptions. is the way that I put it. Okay, example 2. And this is from coffee cooling on a desk, and it asks us to plot the data. Is the function increasing or decreasing? Well, we can see that even from the table that it's decreasing. Describe the function, be as precise as possible. The temperature decreases a little more quickly at first and then more slowly. How I got that was actually, if I look over the finite differences, and the finite differences are when I subtract adjacent y values, right? So I subtracted the adjacent y values. I did the first differences and the second differences, and I can see that it's the temperature is dropping a little more quickly at first than later, which kind of makes sense. If it's really, really hot, it'll cool more quickly at the start. And then I calculated some rate of change, right, from the table, and that matches what we were talking about. And what type of functions does it appear to be? Well, notice that because the second differences are constant, it looks like it's a parabola perhaps, right? And that's what I've said. Since the second differences are constant, it appears to be a parabola, but this doesn't make sense since the temperature wouldn't increase again. So yeah, the coffee is cooling, but the coffee's not going to spontaneously warm up again. So it doesn't really make sense that it's a parabola. And then part E is, what other function type could be used as a possible model? Well, this, if you remember from last year, is actually an exponential model, right? A coffee cooling to room temperature. And I can tell it's an exponential model by not taking the differences, but by calculating the common ratios. 47 divided by 55, and you get the common ratio of a 0.85, a decay function about. And that makes sense because a exponential function will have some sort of asymptote there and decrease to its asymptote, and this asymptote will be room temperature, whatever room temperature might be, 20 degrees Celsius, right? That makes more sense than having a coffee spontaneously heat up. A bit silly. All right, on to example 3. This is Farn swimming back and forth in a pool. Draw a rough sketch, and hopefully your rough sketch looked like something like this. Yours might not be as curvy as mine, but certainly when she gets near the wall, she has to slow down. It's not like she bounces off the wall, right? So there's going to be a little bit of a slowing down there. What type of function is this? Probably some sort of sine function back and forth. Over what intervals is the function increasing or decreasing? Notice that I used the interval notation there from 0 to 60 and from 120 to 180, increasing and so on, and then decreasing on those. When she's swimming away, of course, the distance is increasing. When she's swimming towards the coach, the distance is decreasing. There's maxes of 50 meters away at 60 and 180, and you could follow those patterns. If she keeps swimming laps, it'll be back and forth forever. So there could be many, many maximums and many, many minimums. Minimums of 0 at the start. She starts the same end as the coach, and at 120 and 240 and so on. And the last one, second, not even second last one. When Farn speed is the greatest, that's when the graph is the steepest, right? It's the biggest change in distance over a period of time. And you figure if she's not coming away from a wall and speeding up, or she's not slowing down because she's going into a wall, that's when she'd be the fastest. Well, that makes sense. Somewhere in the middle of the pool, she'll be the fastest. And probably there's a big chunk of time there where she's traveling at a constant speed. What does it say? When is Farn speed equal to 0? Velocity is 0 anytime it's a minimum or a maximum, right? Minimum at 0, 120, and 240, a maximum at 60 and 180. That's when she's turning and going in the opposite direction. This is when she's turning at either end of the pool and her distance isn't changing. And then the last one was to think of what happens if she was in a shorter pool. The maximum would be 25, decreasing the amplitude of the trig function, right? Because she doesn't get as far away. Also, since she can still swim at the same rate, her lap time would decrease as well. So, probably since she's swimming half the distance, probably it would take her about half the time as well. And so instead of 50 here, we'd have, get different color, we'd have 25, and probably, even though it still takes her the same amount of time to turn, so maybe she couldn't swim the shorter pool in half the distance, but it would be pretty close. All right, good. That's that. Um, how are we doing for time? I think I'll probably pause and go into yeah, I'll go into the lesson part of the video in part two.